All right, so now that we've defined big O and we've explored big O a little bit, it's time to define big omega and big theta. So as I mentioned before, the big O in omega, in big O, that O is actually Omicron, the Greek O. So big omega is another Greek letter, and big theta, so theta is another Greek letter. So this is capital omega and a capital theta. First, big omega is defined really very similarly to big O, except with this major difference right here. This is the difference. In big O, that was a less than or equal to, but with big omega, that is a greater than or equal to. Okay, so we still have our witnesses, C and K, and it's defined as a set of all functions f which are greater than or equal to this C multiple of g of x. So if big O is giving you like an upper bound on the growth of a function, big omega is giving you a lower bound on the growth of that function. So for example, like 2 to the x is big omega of x. Okay, we learned that x is big O of 2 to the x, and so vice versa, 2 to the x is going to be big omega of x. And x, in turn, is going to be big omega of 1, because x grows faster than 1. Okay, so there's a couple of examples. Now, here's some questions. A couple of questions here. And this is just to kind of get you thinking. What function, give me an example of a function that is not big O of 1. Okay, what would be a function that is not big O of 1? We're going to get to that in a minute. And what function is not big omega of 1? Okay, so this is important. Comparing things big O or big omega to the constant function 1 is kind of important, because the idea of a constant time operation is something we're going to be grappling with in in section 3.3. We're going to be thinking about what is a constant time operation, and we're going to count things in terms of constant time operations. So the big O of 1, or rather being the same order as 1, is what it means to be a constant time operation. So ponder these two questions, and then I'll come back and answer those at the end of the video. Okay, so let's see. Now we've defined big omega as the set of things that are bigger. Let's define big theta. So not bigger, but no less, rather. I said bigger, but I should say no less than. Big theta is the intersection of these two sets. So you take big O of g of x, intersect with big omega of g of x, and that gives you the set of all things that are both no smaller and also they grow no slower and also grow no faster. So then they are growing the same. Okay, it's like if you're greater than or equal to and less than or equal to, you must be equal, except it's not saying that these functions are equal, it's saying that their growth is equal. In fact, what you can show is that they are of the same order. Okay, so here's a couple of facts that you might want to prove in exercises. Okay, check the homework. Some of these things you're going to prove in exercises. Okay. Turns out if one function f is big theta of g of x, then you can be guaranteed of the opposite. G of x will be big theta of f of x. Okay, and then f of x is big theta of g of x if and only if f of x is big O of g of x and g of x is big O of f of x, which means that they are the same order as we defined earlier. Okay, so big theta is stating that two functions are of the same order. Okay, so like for example, like x squared is going to be big theta of 5x squared plus 2x minus 1 or something. Like any two quadratic polynomials are going to be big theta of one another, right? Even if you take two quadratic polynomials and add things, like say you add a logarithm to each of them, those are still going to be big theta of each other because they are big O of one another as well. So that's what it means for two functions to be the same order. We have the specific notation for that, which is theta. Okay. So that kind of just builds on the definition of big O and gives us this extra, a couple other extra notations for talking about things that are of the same order. Now, I do want to come back to this. So what does it mean for a function to be not big O of 1? Well, if 1 is a linear function, right? Here's 1. Let me use Here's 1, okay? If you want something that's not big O of 1, then what that means is that there's no multiple of 1, which is going to be serve as an upper bound for that. So, that's why sine of x or any multiple of sine of x wouldn't work, because you can always raise this bar up by multiplying this function 1 by something. That's the c value, right? And get something that's going to bound it above. So what you need to be something that is not big O of 1 is you just need any function that grows without bound. So an easy example of that would be like f of x equals x. So we could say as our answer here, what function is not big O of 1? Well, f of x equals x is an example of something that grows without bound. Any other function that grows without bound is going to be big O of 1. Now, what function is not big omega of 1? So now big omega says that big omega says that you can make this a lower bound, right? So if something is going to be big omega of 1, then it means that you can lower this bar. You can lower this bar to be beneath it. One thing we could do to find a function that's not big omega of 1 is take the reciprocal here. We need something that like gets arbitrarily close to 0. Essentially, we need something that has a horizontal asymptote at 0 over here. So so the easiest example of that is 1 over x. Okay, g of x equals 1 over x. Is an example of something which is not going to be big omega of 1, because no matter how low you make this bar, you can never be lower than this entire function, because this function gets arbitrarily close to 0. So these are sort of opposites of each other, right? This is getting arbitrarily close to infinity, and this is getting arbitrarily close to 0. Okay, and that's what it means to be not big omega of 1. So that's our answer there. These are not the only possible answers you could give. If anybody has other answers they came up with, I'd be happy to discuss them. I think this exploring this is a nice way to grapple with these definitions and these notions of growth. So there. Okay. That pretty much does it for section 3.2. So next we're going to move on to algorithms and how we can use these ideas of big O and big theta in particular to like sort of discuss the growth rates of algorithms.